Welcome you all. In this section, we are going to discuss about the consequences of multicollinearity problem. The consequences of multicollinearity. The consequences of multicollinearity problems can be is theoretical consequences, and the other one is the practical consequences. Let us see what are these theoretical and practical consequences of multicollinearity. That is, one of the important theoretical consequences of the multicollinearity problem is that even in the case of the multicollinearity problem, the unbiasedness property will not be violated. And the second one is the collinearity doesn't destroy the property of minimum variance. It is also true that collinearity does not destroy the property of the minimum variance. In the class of all linear unbiased estimator, the OLS estimators have minimum variance. That is, they are efficient. That we have already learned about that. But this doesn't mean that variance of OLS estimators will necessarily be small in any given sample. But this doesn't mean that the variance of an OLS estimates will necessarily be small. And the second important consequence, second theoretical consequence is that the collinearity doesn't destroy the property of minimum variance. The third one is that multicollinearity is essentially a sample phenomena in the sense that even if X variables are not linearly related to the population, they may also be related to the particular sample at hand. That means multicollinearity is essentially a sample phenomena. Because even if the X variables are not linearly related to the population, they may be so related in the particular sample. They may be so related in the particular sample at the hand. When we postulate the theoretical or population regression function, we believe that all the X variables included in the model have a separate or independent influence on the dependent variable Y. This is the theoretical these are the theoretical consequences of the multicollinearity. That is, in the case of even in the case of the multicollinearity, OLS estimators are unbiased. Second one, it does not destroy the property of minimum variance, and it is a sample phenomenon. And the third consequence is that multicollinearity is essentially a sample phenomena in the sense that even if these X variables are not linearly related to the population, they may be so related to the particular sample at the hand. These are the theoretical consequences. Let us see the practical consequences of multicollinearity problem. Some of the important practical consequences of the multicollinearity are although blue, the OLS estimators have larger variance and covariance, making the precise estimation difficult. We have seen that even in the case, or one of the theoretical consequences of the multicollinearity was that even in the case of the multicollinearity, there will attain the minimum variance, but these variance and covariance won't be that much small, and it will be larger variance, making the precise estimation difficult. Second one, the confidence interval tend to be much wider, leading to the acceptance of zero null hypothesis. That is, the true population coefficient is zero more readily, or there are every chance of accepting the type 2 error. The confidence interval tends to be much wider, leading to the acceptance of zero null hypothesis. Third one is the T ratio of one or more coefficient tend to be statistically insignificant. That is, T ratio will tend to be statistically insignificant. And fourth one is that although the T ratio of one or more coefficient is statistically insignificant, the R square, the overall measure of goodness of it, can be very high. That is, even though T values are insignificant, the R square will be very high. That is, the model will be a good fit. The OLS estimators and their standard errors can be sensitive to small changes in the data. That we have already seen that it is a sample problem, and therefore the OLS estimators and their standard errors can be sensitive to small changes in the data. These are some of the important practical consequences of multicollinearity. That is, although best linear, unbiased and efficient estimators, the OLS estimators have larger variance and covariance, which make it difficult to make a precise estimation or precise estimation. The second one is the confidence interval tend to be much wider. Third one, the T ratios of one or more coefficient will be insignificant. Fourth one, even though T ratios are insignificant, the R square will be very high, or it shows a good fit. Then fifth one is the OLS estimators and their standard errors can be sensitive to small changes in data. Then the first one is the larger variance and covariance of ILS estimators. Summation sigma, the variance of beta 2 cap equal to sigma square divided by summation x 2I square into 1 minus R23 square, and likewise variance of beta 3 cap and covariances are given here. And here R23 is the coefficient of correlation. R23 is the coefficient of correlation between x2 and x3. It is clear from this equation that as R23 tend towards 1, that is, if R23 tend towards 1 means collinearity increases, the variance of two estimates increases, and likewise the covariance, if R23 increases, the covariance also will increase. That is, the larger variance and covariance of the OLS estimator is we will get a larger variance and covariance for the OLS estimators, even though the estimators are blue, is one of the important practical consequences. Here the variance, the formula for estimating variance of beta 2 cap, variance of beta 3 cap and covariances are given. Here R23 is the coefficient of correlation between the two variables, and here this coefficient of correlation shows the relationship between two variables. If it tends towards 1, we can see that this value will tends to be large. Variance of beta 2 cap, variance of beta 3 cap and covariance will obviously it will increase. The speed with which variance and covariance increase can be estimated using the various inflating factor. Another important term is the various inflating factor. What is this various inflating factor? The speed with which variance and covariance increases can be measured through the various inflating factor, and it is defined as various inflating factor equal to 1 by 1 minus R23 square. And variance of beta 2 is given as sigma square divided by sigma x2I, and here in the previous one the variance of beta 2 cap is sigma square by sigma summation x2I square into 1 minus R23. Here variance inflating factor is this component 1 minus R23 square. Therefore we can write this as sigma square by sigma x2I into variance inflating factor. This it's given here, and similarly beta 3 cap sigma x2I sigma square some x3I square into variance inflating factor. And here the variance inflating factor shows how the variance of an estimator is inflated by the presence of multicollinearity. That is, how much is the increase in variance how much is the increase in variance due to the multicollinearity is shown through the various inflating factor. As R23 square, this one, as R23 approaches 1, the various inflating factor approaches infinity. It is very clear from this. If it is 1 minus 0, 1 minus 1 is 0, 1 by 0 is infinity. Here as R23 square approaches 1, the various inflating factor will turn to be infinity. If there is no collinearity between x2 and x3, various inflating factor will be 0. That is 1 by 1 minus 0. That is 1 by 1 equal to 0. If it is 1, then it will be infinity, or if it approaches to 1, it will increase and finally it will reach to infinity. If there is no collinearity, then various inflating factor will be 1. That is 1 by 1 minus 1 equal to 1 minus 1 is 1 minus 0. That is, if there is no collinearity, it will be 0. That is 1 by 1 minus 0 gives 1. These are the two conditions. This various inflating factor, the first one is that the the problem or the practical consequence of multicollinearity is that the variance and covariance will increase. Variance and covariances are given here, and the speed with which it will increase is given through the variance inflating factor, and this variance inflating factor is defined as 1 by 1 minus r23 square, that is 1 divided by this component 1 minus r23 square. As r23 square tend towards 1, the collinearity increases. Here the r23 is the coefficient of correlation. As it approaches towards infinity, as it approaches towards 1, this collinearity will increase. If there is perfect collinearity, the variance inflating factor will be infinity. If there is no collinearity, the variance inflating factor will be 0. This is the first one. Here the statement that as variance increases, or as the value of R23, the coefficient of correlation increases, the variance inflating factor also will increase. Here in accordance with the value of value of R23, its variance inflating factor is 1 minus 1 by 1 minus R23 square. Then we will get these values, that is, as the collinearity increases, the variance inflating factor will increase, and it is shown through this figure. That is the behavior of beta 2 cap as a function of the R2. In this figure, the behavior of R23, in this figure, the behavior of variance of beta 2 as a function of R23 is given. That is, a variance as a function of R23 is given, it will increase. The variance of I cap, the variance of the kth coefficient can be estimated as follows. The variance of beta I cap equal to sigma square by the summation xi square into 1 minus 1 by 1 minus ri square. Here beta I cap is the estimated partial regression coefficient, r j square equal to r square in the regression of xj on the remaining k minus 2 regression. Then the variance of beta I cap equal to the variance of beta I cap equal to sigma square divided by summation xi square into the 1 minus variance inflating factor. And this is the general formula for the kth variable, that is variance of beta I or beta k cap equal to sigma square by sigma xi or xk into variance inflating factor of that variable or that estimates. And the inverse of this variance inflating factor is known as the tolerance limit or the tolerance, simply tolerance. That is the inverse, the speed with which the variance increase is shown through the variance inflating factor, and the inverse of variance inflating factor is the tolerance. That is, tolerance equal to 1 tolerance of ith estimator equal to 1 by variance inflating factor of that estimator, that equal to 1 minus rj square. When rj square equal to 1, that is perfect multicollinearity, then the tolerance will be equal to 0. That is, in the case of the perfect multicollinearity, the tolerance will be 0, that is the inverse. And when rj square equal to, there is no collinearity, tolerance will be 1. The next important practical consequence is the wider confidence interval. Because of the larger standard error, the confidence interval for the relevant population parameter tend to be large. Hence, the consequence of this is that the probability of accepting a false hypothesis, that is type 2 error, will occur. This is the theoretical problem. This is a practical problem associated with wider confidence interval. In accordance with the various coefficient of correlation, the variance inflating factor as given earlier is given here. In accordance with the confidence intervals constructed for here, in the case of the 0 here, the variance inflating factor is 0. Then in the case of the if there is no correlation, the confidence interval can be estimated at beta 2 cap plus or minus 1.96 into 1 root of sigma square by sigma x2i square. If the correlation is 50%, then the variance inflating factor is 1.33, that is beta 2 cap plus or minus 1.96 root of 1.33 into root of sigma square by sigma xi square. That means as the collinearity increases, the confidence interval also increases. Then next one is insignificant t ratios. That is, here a t ratio is defined as beta 2 cap by standard error beta 2 cap for beta 2 beta 1 cap by beta 1 cap divided by standard error beta 1 cap for beta 1. In the case of the high collinearity, estimated standard error increases dramatically and thereby making the t value smaller, and accept the null hypothesis that the relevant true population value is 0. That is, in this case, we will get an insignificant. If multicollinearity problem exists there, the t values will be the t values of some of the estimators will be insignificant. This is another practical consequence of the multicollinearity. That is, we will get a high R square value. The high R square implies the goodness of fit. At the same time, some of the variables won't be significant. This also creates problem, or this is another important problem of the multicollinearity. These are the consequences of multicollinearity. That is, we explained the theoretically the multicollinearity. In the case of in the presence of multicollinearity, the OLS estimators are unbiased. Then second one, collinearity does not destroy the property of minimum variance. Third one, it is a sample phenomena. Then we examined the practical consequences, like although blue, the estimators have larger variance and covariances that we have seen. And the second one, the confidence that is explained through this explanatory variable and the speed with which the variance increase is given by the tolerance limit, is given by the variance inflating limit, the variance inflating factor, and the inverse of it gives the tolerance. Then next one is the confidence interval tend to be much wider, leading to the acceptance of type 2 error. Then second one, t ratios of one or more coefficient tend to be statistically insignificant. Fourth one, even though t values are insignificant, the R square will be very high. Then another one, the OLS estimators and their standard errors can be subject to small changes in the data. These are the practical and theoretical consequences of multicollinearity.